So I'll just name this as class notes and I'll start. Just let me know if you're able to see this. Hope I'm audible and you're able to see the screen. I have not shared my screen. Well,
Yes, sir, you are audible.
I wish
Screen,
to
I think you
share
have
my
not shared
screen.
yet.
Yes, I hope my screen is visible now.
Yes, sir,
Yeah,
yes, sir.
sir.
Yes,
Yeah.
visible.
Sorry to interrupt, respected organizer, coordinator, sir. So is recording started, sir?
Yes, yes, sir,
Yes,
started,
it is
yes.
started. It is
Because
started.
previous session was late in recording, sir. Sorry to say.
2-3 minutes it was late. Yeah.
Thank you, sir.
So I'll just start with agenda. We need to talk about the need for response surface methodology, RSM we call it as, and then we would see steps in RSM. Third, we will talk about the CCD, central composite design, and fourth we will talk about box banking design. Okay, so this is what we will cover, and we'll try to finish the session in the stipulated time. See, last two sessions, Hemant sir has talked about full factorial and fractional factorial designs. Now, the interesting part about this design is that we are trying to find out solutions for responses, which is, suppose this response is y, and this would be given by some function of factors. Okay, so these are nothing but the y's that you would be having. Now, the interesting part is both full factorial and fractional factorial designs, they assume that the relationship between x and y is linear relationship. So may it be, I mean, it's a multiple linear regression that we do. And this is usually given by y is equal to, suppose if I have four factors, x1, x2, x3, x4. So I would have some main effects, which is given by m1, x1 plus the m2, x2 plus m3, x3 plus m4, x4 plus then I can have the interactions m12 with x1, x2, then so on and so forth, and then the constant term. So I can have interactions and I can have the main effects given here. Now, all of these assume that the relationship between x and y is linear. Now, life is not so simple, and technical life is definitely not simple. So there could be some y's which are dependent on x's, wherein the relationship may not be linear and it could be non-linear relationship. Now, in such cases, we need to analyze the nonlinear responses, and the optimization method which is commonly used is known as response surface methodology. Now, when we say nonlinear, what could be the different relations? The different relationships can be polynomial, can be cubic, can be exponential or can be power. So there could be a polynomial with power 2, polynomial with power 3. So this is quadratic. This could be cubic. There could be exponential. There could be logarithmic. There could be power law. So all of these are possible. So response surface methodology is primarily for analyzing the nonlinear responses, nonlinear relationship. A simple example, if I have to give, is, we are in winter season. So let's say the comfort level of human being is function of temperature and humidity. Okay. Now, if I have to see the relationship between comfort and temperature, I would be having less comfort. If this is on x-axis, I have temperature, and on y-axis, I have comfort. As for extremely low and high temperatures, I would have less comfort, and there would be an optimum comfort that I would have at certain middle temperature. Similarly, relative humidity, I can have extremely low humidity, extremely high humidity, I can have a relationship like this. And the response surface that will be made, which, for example, if you just imagine a surface plot, something like this. On y-axis, I have comfort. And here I'm making a plane like this, which represents here temperature from low value to high value, and humidity from low to high. I would probably get something a surface which probably would look like this. I'm not good at drawing, but this is how I would be able to see the response surface, or probably something like this. So this is the response surface I would get, and I need to find out the optimum temperature and humidity that will give me the best settings of temperature, and humidity for optimum comfort. So pardon me for my handwriting, but hopefully you're able to understand what I'm talking. So this is what we have to understand. Okay, this is in very simple terms that I'm trying to tell you the relationship, non-linear relationship between the factors and the response. Okay, now if we go further, so this is the need. This is the need for the response surface methodology, and we need to analyze this nonlinear relationship. Okay, now how do we do it? What are the steps in doing it? So we need to understand the meaning of response surface. When I say response surface, just to clarify further, I think you must have been covered with the contour plot and surface plot. I'll just do that once again. Was that covered yesterday, today?
Yes, sir, covered.
Yes, so I'll just draw a contour plot quickly, and then I'll start with the discussion. So I'm just taking some example here in Minitab. Define this, the factors, temperature. Just give me a moment. Low, high are chosen value. Uncoded designs and specify. I'll repeat this once again. I just want to do that. And I go to start DOE factorial and analyze factorial design yield. Click OK. Yeah, this is analyzed and I can directly go for the system. Okay, so I'll just give me a moment. Should show me the surface plot. Wait a minute. Yeah. Right now, I'll just copy this. This is what you would get the surface plot as. And what we see here is known as the response surface. Okay, so this is an example for temperature and reaction time. And what we get here is the response surface. This is how the response surface looks like. So that is just to give you some feeling there. And if we do the contour plot of this, it would probably, not probably, it would look like this. The contour plot would be something like this. On this axis, I have the factor 1 and this is factor 2. And there would be low and high settings of this. Okay. And and one would get the some. So this is the region and you would have the response lines like this for such particular thing. Now this is these are the zones that you would get for for the settings of the factor from low to high, factor 2 to low, from low to high, and for factor 1 to factor 1 low to high, you would have the various bands of responses, and you will find the response will have certain values depending on the nature of the response. Okay. So you would see the contour plots something like this. So this was just to make you aware of how the response surface is seen. Okay. So response surface is the variation or the values of response with respect to y, and it can be given as function of. So the response surface eta can be given as function of various factors x1 to xn. So with this, let us now proceed to the steps in response surface methodology. So Now, let's understand this with an example, and I'll just take you to that example. This was covered. Yes. Let's say a chemical engineer is interested in finding operating conditions that will maximize the yield of a process. The current settings are the reaction time, 35 minutes, and temperature as 155 degree. Now, yield here is Y, and the factors here are reaction time and the temperature. And the current settings of this are 35 and 155, and the current yield is 40%. And one wishes to maximize this yield. Okay, he wants to improve the yield and decides to conduct design of experiment using current settings as center point and factor and factor levels. So around this 35, so I have reaction time here and I have temperature here. So the low setting for reaction time is 30 and high setting is 40, and this current setting is the center point for the, so this is 35, 155, and here the lower temperature is 150 and the upper temperature is 160. So these are the four corner points of the design, and this is the center point. Okay, so and then using this he would probably do the experimentation, and he would get the response, what is the yield that he would get. And let us put this values of yield in Minitab and just see let's see how it can be done. So I'll just go back to Minitab. So let's say I do DOE factorial, create factorial design, and number of factors 2, and design 4. There is only one option available, and I take center points as number of center points as 5, and click OK here, and then factors I put as reaction time. I'll say just time, and this is temperature. Low value is 30, high value is 40, and temperature is 150 and 160. Okay. And options, I don't randomize the runs. Click OK, and results will be there. Click OK, and I get these runs, and I write down the yield here. And yield I can copy it from the Excel file that I have. So this is, these are the first 4 runs: low, high, high, low, low, high, high, high. And then these are the center point, the 5 center points, 35, 155, which happens to be the current settings of the design. Okay, so I'll go to Excel and use the yields that are given here. So 30, 40, 150, 150. Let me just check whether I'm right. I think that's right. 30, 30, 150, 60. No, I'm making a mistake here, looks like. I'll just change it. The sequence might be hampering the thing. Should be this way. Hopefully now it is correct. Yes. I just made a mistake because the sequence has to match, because the while I'm taking these values, it should match. That's it, nothing else. Else my references would go incorrect. So this is the yield that I got. And now you can see here, these are the corner points, and this is my center point, and there are 5 replicates that I have taken, and this is the yield that we get. So now this design can be analyzed. So we can analyze the factorial design, and yeah, I can analyze this and go to graphs and say 4-in-1 here, click OK, click finally OK. And this is how it can be done. So I get results like this. So we can have the factors designed here like this, and center points are included in that. We get the Pareto like this. So we can see here that both the factors, factor temperature and factor reaction time, are significant, and the interaction is not significant. And if we go to the session window, if we go to the session window, we can see that this is the analysis that we have here. I can just copy it here in Minute tab. Sorry, in Excel and for no. So we can see the analysis here, that we have analysis of variance here, and we can see the 2 main factors, temperature and time, and there are 2 factor interaction, and curvature is seen over here. And we can see as of now that if we wish to understand the coded coefficients here for the equation, we can get this. We can have the coefficients here. Now these coefficients mean these are the slopes for, these are the slopes, and this is the constant here. So I can have an equation y yield in this fashion. So 0.325 temperature, 0.775 times time, minus 0.025 temperature into time. Okay, and then I can have the constant, which is 40.425. Like this, there can be these are the coefficients that I have, and I can get the multiple linear regression here. So this is the equation in coded coefficients, and in uncoded, that means in the original units, you can have this. I forgot to add center point here, 0.035. Are you asking questions? There are so many things in chat. No. Sorry. Sorry for that. If you have any question, please speak in between, because I'm not, I won't be able to see that. Okay. So this is the equation that I get. And this is the equation that I get in uncoded units. Now, interestingly, if you see here, the center point, the curvature that I have seen, I have added here, the center point is not significant. We always look at the p-values here, and we can see that the interaction and the curvature, the center point is not significant. That means there is no, between the two settings, 30 to 40 and 150 to 160, there is no there is linear relationship that exists. The curvature is not significant. So when we will call that curvature is significant, if this is the linear relationship that we have for low 30 and 40, so if the center point response is far away from the line, then there is probability that there would be some non-linearity that exists. But since the center point is very close to the line, we can see that the curvature is not significant. Now, how do we find out that? Now, that is by numerical values. And now, if we see the factorial plots, if I just draw the factorial plots and I plot the, I draw the factorial plots here and see, sorry, I go to graphs and plot the main effect and interaction plots. So I say click OK. And this is how the main effects look like. So if you see here, the center point, the response at center point is very close to the line. Here also it is very close to the line, and here also we can see it is just at the middle. Okay, so that means the relationship between these 2 points is linear, and that is validated, and that's why the p-values here are, the p-value here for the curvature is very high, and hence we say that the center point is not significant. Okay, so this is at the initial setting. Okay, we are just starting the experiment. So now, what is my interest? So this is in the beginning. Okay, so my interest is, as I increase the temperature and increase the reaction time, the yield increases. So I will go to a point, wherein, it reaches the optimum point, and I wish to find that. So what is the mechanism to do that? And that mechanism is known as method of the steepest ascent. Okay, so let's understand this concept so that we can move further. Okay. So here, as we were discussing, center point is not significant, and the coefficient of temperature and time are, for coded coefficient, is 0.325 and 0.775. Okay. Here also we have seen in ANOVA the curvature is not significant, and main effect plots we just plotted. Change in reaction time has greater benefit is what we have seen. Interaction are, since the lines are parallel to each other, interactions are not evident. Lines are parallel. This is Q plot. Residual plots also we have seen. Now we can reduce the model, I will skip this reduction in the model. Probably I'll just complete now. So I can remove the center point from this. So I go to design analysis once again and go to terms and remove the center point from the model and remove the interaction also from the model and click OK and click finally OK. So this is how the new model would be, and I would get the coefficients do not change. Now here the
Sir,
yes, please.
what was the reason for removing the center point?
Since it was not significant, I would not use that
Okay,
here.
sir.
That's the only reason, nothing else. Now, since the curvature is removed, the p-value, these are only two things. The interaction is not part of there, and it is just there now. We go further now. So let me. Now, what I wish to see here is, if you see here, now I will get the contour plot here. I can get the contour plot and I get the contours not required, cancel options also. So I'll just have, since there are only two things, this is the contour plot that I get. Okay, and these are the bands of the yields. Okay, the darkest point is higher. This is the point where I get the highest yield, 160 and 40. So I'll just copy this graph. This will be useful for me. Now this is the region 150, 160, 30 and 40, and this is the center point that I have here. So 35 and 155 somewhere here. This is the center point, and these are the two things. Now I wish to take this becomes my current region of experimentation. I wish to take this. This is my current region, and I'm going to increase the temperature. I know that on this side it is increasing. So what is the direction of improvement? That direction of improvement I need to understand. So this is time and this is temperature here. So gradually I need to increase temperature and increase time and see that I will get the maximum yield. Why in this direction? Because maximum yield, this is if you see this band, it is 41.5 here. So this side it is having higher yield. Okay. So this is my direction. Now let's see how I go further. So I need to increase time and temperature. And by what graduation I do that I need to find out. And that method is nothing but method of steepest ascent. So let us see that. So we need coefficients for yield in uncoded units. Now here, the coefficients for the yield are for uncoded units are like this. And from where we got this? We got this from the equation that we got here. Equation for the uncoded, no, not here. I will just make use of this. There was these values. Yeah, here it is. No, wait. Control. Yes, there we go. This is the regression equation that I got. Now for the reduced model, I got the, and this is in the coded terms, and these are the coefficient in the uncoded terms, 0.065 for temperature and 0.155 for time. So these are the coefficients in the uncoded units, and these are the coefficients 0.325 and 0.775 in the so now we should be using this. We should be using, so this is slope. This 0.065 is the slope, delta y by delta x, and this also is 0.155. This also is the slope. When you are dealing with temperature, there is delta of 20 here. Yes, this is sorry, 10, the delta of 10, and this is also delta of 10 here. Okay, so that's the slope I get, and now I make use of this. I'll just go to slides again. Yes, here we go. So I get this slope in which the in the direction of improvement. So this is 0.155 divided by the 0.065. So on the control plot, there is the slope in which this see, on x-axis you have the time here. I'm sorry. Just a minute. Made a mistake. Yeah. No. So this is absolutely fine. I have time here on y-axis, and I have temperature here on x-axis. Now this part, so delta y, so slope here is delta y by delta x, which is this coefficient 0.155, which is on y-axis. So that's why it is 0.155, and this is 0.065. This is the slope, which is 2.3846. And you can have you can also find out, since this is equal to tan theta, you can find out this corresponds to 67.25 degrees. And here later you will find that this is the direction, path of steepest ascent. Okay, so here you had the center point 35 and 155. Sorry, this was the center point, and this is where you started. And now in this direction you will move and reach to another setting, which is you will have the incremental values for the temperature as well as the reaction time. Okay, and by how much you can decide for one and find out for other. Okay, suppose you decide to have increment of 5 minutes in time, corresponding delta in the temperature can be found out by this relationship, which was this slope. Okay, so this can be determined, and you can have sorry. So we need to move along this steepest ascent. So we have started with this at center point of 35 and 155, and we got yield of 40. Now with that delta 5 minutes delta for time, and corresponding delta here by 2 each. That 2.38 is approximated to 2 here. So this is the origin plus 1 times delta, which is 5 here and 2 here. You conduct this trial, and see the yield here. Okay, so you proceed for the further one and look for any change in the response. Okay, now as you go ahead here, so what is happening, friends? If I just see here, or I will just able to explain. Yeah, here it is. So on y-axis I have yield and then reaction time here. I'm just giving increment of 5 for reaction time, and as you can see, yield goes on increasing. For temperature also, the increment of 2 is given and the yield keeps increasing. And there is a point here at this point wherein, it reaches the peak and then it starts falling down again here. So that means this change is the change which is of my importance. So this region is very important for me, wherein I'm able to see the the optimum region. Okay, so this optimum region here is, you can see here the yield is maximum at this point. Okay, and so this 85,176 is the center point here, and you can see here it is 77.6 and 76.2. So that means the yield is dropping like this. So this is the region which is of importance to me. Okay, so with this center point, now this is the region wherein I need to design. So by using the steepest ascent, we are trying to determine this region. So I got this region 80, 90, 85. So this is the region of my further experimentation for optimization. And that region also is seen over here. So this range is important, 80 to 85, and here it is this region which is of importance. So moving along the path of steepest ascent will take us closer to the peak, but this does not guarantee that it will reach the peak. We therefore need to explore this region to find the optimum setting. So at least we got the region, and this requires checking of steepest ascent again and curvature check. So what do? We now perform the same experimentation, but at settings which are 80 and 90 and 165 and 175. So that we have that region, and then 85 and 170 are the center points. So this is wherein we will see whether the curvature is further significant or not. That we need to check. So now I'll stop at this point and ask for questions if there is any, so that I can go for the further part.
Sir, this is like a sort of exploration, right? Sometimes
Yes,
it may
it
end up
is.
in linear relationship as well.
Yes, it might, but then what should your technical knowledge about the relationship between response and the factor is of prime importance.
Yes, sir. Yes, sir.
Everything cannot be statistical or mathematical. There has to be some technical intelligence, and the things that we should rely on is our technical intelligence. For example, the initial example that I given, temperature, humidity. We as human beings know that higher temperature, lower temperature doesn't suit us. Higher humidity, lower humidity doesn't suit us. So there is an optimum region that we have. So this technical knowledge is there, is assumed to be there.
Okay. So it is done after initial approach, right? Typically.
Yes. So it is, that there is a region, that there is something of this sort is available, and then you are trying to determine the exact portion or exactly region.
Okay. Thanks, sir. Excellent insights.
Yeah. So now
Sir,
let us. Yes,
can I
please.
ask a small question, sir?
Yes,
So
please.
we are able to understand what is actually you're doing it. But in a practically, actually, because we are from management faculty, we are just new to these platforms. So how you start
Okay.
understanding these platforms or model? It's a beginner, I'm asking.
Beginner is see, there are many things in real life scenarios. May it be not technical also, right? We are discussing some chemical engineering here.
So more specifically, we
Yes,
understand
please.
what you're doing it actually, but they are very difficult to follow the procedure you carry out while doing apply all the functionality, right?
No, it is not difficult.
No, from a point of view, from my side.
No. See, when we say difficult, it means it is. See that if it is important for you to find out the optimum regions,
Exactly, sir.
you would neglect the difficulty part. If it is critical, you would give it your best efforts to arrive at the optimum things. If it is critical to cost, if it is critical to time, if it is critical to quality. So irrespective of whether I'm a chemical engineer or industrial engineer or manufacturing engineer or a politician, it doesn't matter. If it is critical to cost, critical to quality, critical to time, and it needs to be done, optimum regions needs to be found out, I must do this. So that's
Okay,
again
okay.
the business intelligence that will prevail more than what we are doing statistically.
Yes, sir.
Yes. See, I'm just trying to say here at this point, I'm answering two questions there. First, I answered the technical intelligence, and now I'm answering that business intelligence is more important than whatever we are trying to do.
So actually, I understand the question and all is very clear. But when you applying the statistical part, no, that is very difficult to
Sir,
follow it. That's why I'm saying.
if see, it is difficult to follow. It is not compulsion that we should do it. People without doing statistics, they are able to optimize. So those things are available. But if you wish to replicate it somewhere, this will help. This will increase the finesse of the output that you are getting.
Yes, sir.
And
Yes,
when the cost is very high, the finesse is important.
yes, sir.
Yeah. So we cannot be approximate in some situations.
Sir,
Sure.
sir, can I ask a question, please?
Yes, please.
So let's say that we have three factors and one
Okay.
dependent variable. And
Okay.
I am from actually finance background.
Fine.
Okay. So from that particular point of time, I am just taking three factors. The three
Okay.
factors I am taking from social media study, a social
Okay.
media study. Right. That first factor is type of, you can say, post. Is it of sports, entertainment, or say normal category politics? Okay.
Okay.
Then
Yes.
post time, that what is the duration of the post?
Okay.
Then length of the post, say whether it is running into pages or only small snippets. And last is hits. Because generally in social media, people try to follow the number of hits that particular post has got. Okay.
Okay.
So our hits is the decision variable, actually the main response variable, and all other things are factors. So can we
Yes.
apply this kind of, you can say, design of experiment over here or response surface methodology?
We can apply, but in such cases, what they apply is conjoint analysis, wherein it is similar to the experimentation, but the term that they use is conjoint analysis, wherein it works with different levels, and a solution seeking is done. So, but if the responses are non-linear, you finally need to come to this only. So yes, it can be done.
Sir, is this applicable for continuous variable only, right? RSM?
Output variable continuous.
Yes.
You can have categorical variable in factors.
Okay.
Yes.
And initially it was assumed to be linear, right? When the first trial, first it, then slowly we are moving towards the response
Correct. So we
surface, right?
wanted to find out what it is actually, whether the at that point itself the curvature is significant or not. So the curvature was not significant in that area.
Okay.
Okay. And then we moved on that snippet ascent.
Sir, I am
Fine.
having one question.
Sorry.
Yeah, I am having one question, sir. So right
Yes,
now,
please go ahead.
we are manufacturing the liquid silicone rubber molding machine, where we are having a curing time
Okay.
as a means for an example 90 minutes, and we have to reduce the curing time. And the three input factor is pressure, flow, and temperature.
Hmm.
So with respect to
Okay.
that, I am using this surface optimizer there.
Yes, you can use that. But you first conduct the experiment with these three factors and see whether the relationship, leads to some non-linear. You can have the center point for the settings that you are having, and check whether the center point is significant or not. And if it is significant, then you probably have to go for RSM.
Yes, sir. Thank you. Thank you, sir.
Yeah.
Sir, one more question.
Yes.
Can I ask? Hello?
Yes, please.
Yeah, you talked about the human comfort, the optimum level of temperature and humidity.
Yeah,
Let
that's
us say
just an
that for,
example that I gave it.
let us say in the same, similarly, for different persons, there could be a slight variation. Even in an industrial scenario, maybe for product one, there could be one optimum. For product two, there could be one more optimum. So we need to conduct the study separately, right?
Yeah, if the sorry. Please mute yourself, friend. Yeah, thank you so much. Sorry. Yeah. So if the optimums are drastically different, then probably you have to do it. You have to do it separately. If they are slightly different, it could be portion of the random variation. So that needs to be checked. That's what I would say.
Okay, sir. Thank you.
Yeah. So now I think I should proceed in the interest of time. So now, friends, we have got the new region wherein the optimum settings are to be found out. So I'll use the Minitab RSM2 here. This is what I would use. This is already done, and I will. So this is the new experiment, and this experiment is conducted reaction time temperature. You can see here the low settings were 80 and high settings were 90 for reaction time, and for temperature it was 165 to 175, and the point where it was showing optimum is considered as 85, 170 is considered as the center point. You can see here the center point is given as 0. Okay. And now I'll just go for the custom factorial design and put the factors as reaction time and temperature and low high are chosen here, and designs I'll put center point here and click OK and click OK finally. So now I can go for the analysis part. I'll say yield here and terms. I'll again include the center point and the interaction here. Click OK, the similar procedure. Now here, why I'm doing this, I wish to find out whether the center point is significant or not. If the center point is significant, that means there is non-linear relationship available, and then I will go for the RSM design. Okay, so this is the main effect plot that I got. So this is the factorial regression that I got, and you can see here the curvature is significant here. The p-value is 0. P-value is 0, and the other things are also significant except the reaction versus temperature interaction here. So this tells me that the curvature is significant. Now, this is numerically. I can also go for the factorial plots and see the main effect and the other plots and the interaction plots here. And you can see now, unlike the earlier main effect plot and the interaction plot, wherein we saw that this center point was very close to this line, now it is not. And that's the indication that this is the region wherein the nonlinear relationship is available. Hope this point is very clear. Okay. Now we go further. Yes, this shows the curvature is significant. So we are actually, what we are doing here in curvature, we say that we are performing an hypothesis test here, wherein the null hypothesis is that curvature is not present, and H1, the alternate hypothesis, is curvature is present. So what conclusions are we making? If the curvature test shows that curvature is not significant, then the fractional or factorial designs are adequate. And if the curvature test shows curvature is significant, then we need to use response surface design. Now, this is the point wherein I make a decision to go for RSM, response surface design. Hope this is very clear, friends. And the things that I used here is the main effect plot, wherein graphically it was seen the center point is much away from the the line that was plotted, and the hypothesis test, the p-value that I got is less than 0.05. So at 95% confidence level, I'm saying that the curvature is present, and that makes me think that I need to use RSM, response surface design. So how do we do it? Yeah, this is what we need to use response surface design. Now we go for the various types of response surface designs, and this is the main part of RSM. So there are two methods: central composite design, CCD. So this is CCD. We all know it is popular for something else, but here it is central composite design, and this is BBD, that is Box-Benken design. Box-Benken is the name of the statisticians who invented this. So let's first go for the central composite design. So it is most popular class of designs for RSM. This was introduced by Box and Wilson, and generally consists of 2 to the power k factorial or fractional factorial of resolution 5. It can be used in sequence with earlier factorial designs by adding appropriate axial points and response information. So let's see this. Let us first go for the central composite design. There is a term which is known as rotatability of design. What does this mean? RSM should provide good predictions throughout the region of the interest. Now, region of the interest means wherein the optimum points available. Here, the predictability should be very high. One way to define good is consistent and stable variance of the predicted response at the point. So a design is said to be rotatable if it has same variance of the predicted response at equal distance from the center of the design on the spheres. Now, so what is important here is, you should remember here is same variance of the predicted response. That is, so if you have the same variance of the predicted response at equal distance of the from the center of the design, then we will say that the design is rotatable. So this is the precondition that we have, or the condition that we have. So what is the first type of central composite design? So this is the region wherein you have the optimum part. Okay, so this is your center point, 0, 0, and then there is this is the corner points for your factorial part. Okay, low and high values. So if you just look at this part here, now for this same settings here, 80, 90 and 80, 90 and 165, 175, we should be having, so this is 80, 90. And here we should have the 165, 175. Okay, so this would be 90, 75, and this is 90, 165, 80, 165, and this is 80, 175. So these are your corner points, and this happens to be your center point, which is 85 and 170. Okay, now apart from these points, so these are these are your corner points, or the factorial points, what they call it as. Apart from this, there are these axial points. Now this axis is for x1, the factor 1, and this is for the factor 2. There are axial points here. So these are the additional points. And these additional points are at certain distance alpha. Okay. Now, the number of axial points are equal to 2 multiplied by the number of factors. So if you have 2 factors, there would be 4 axial points. Here we have 2 factors. That's why there are 4 axial points. If there are 3, then there would be 6 axial points. So if you have third factor, you'll have 6 axial points. The number of points in the factorial portion of design is NF, which is nothing but the 4 factorial portion. So this portion is factorial. Factorial means with +1, -1, +1, -1. These are your factorial portion, and these are the axial part. Okay, so recommended distance of alpha for axial points from the center is number of factorial points to the power 1/4. So if my number of factorial points are 4 here, so these are 4 to the power 1/4, which is root of 4 is 2 and root of 2 is √2. So this is 1.414. Okay. And for 2 to the power 3, it would be 1.68. So it would be 8 to the power 1/4, which is 1.682. So that this distance alpha is 1.414, which is square root. Okay. Now, if you just see this also, this diagonal here, this dimension is 1, this also is 1. So the hypotenuse of this is also square root of 2. So if you just see here, you get a circle here, which is of radius √2. Okay, this also is √2. This also is √2. This also is √2. Now this diagram is not proportional, but you will find that this is on a circle. All these points are on a circle. Hope it is clear. Wait. Let me just remove the animation here. So here, so there are many such different designs available. So there are number of corner points here are 4. Number of axial points here are 4. And you take number of center points for better predictability. So total number of runs here are 13. So for center composite design with 2 factors, it is, it is 13. And for three-factor design, the number of corner points are 8, actual points are 6, 2 into k. Then the center points are 6, and total number of runs are 20. Okay, so this is another type of design for three factors. So these are used. So just a minute. I think this needs to be deleted. Give me a minute. So these are the designs available for two-factor and three-factor. Yeah, I think we have covered this as well. Yeah, this is the circle that I was talking about. They are on the same circle. So this is the circumscribed design, what they call it as. Then this part, here it is face center design. Now here, in this case, there are factorial points available. And the actual points are also alpha equal to 1 here. So here, this is face-centered design, and this also is simpler. Here, alpha is equal to 1. Here, alpha was equal to 1.41 root 2. And then there is third one, which is known as inscribed one. So here, these are at 1, and the star points are set as coded level of plus minus 1, while as the factorial points are at so these are at 1. The star points are at us, when the factorial points are at 1 by alpha from the center. So this is at 1 by alpha from the center. So this is inscribed region. Now, why this is important? See, what happens is, 1 times this is 1.41. Suppose this is 90 multiplied by this 1 is 90 multiplied by 1.41 could be some value, and this value may not be possible physically. So choice of these designs would come from the practical aspects, whether you can achieve these values and what region is more important for you, whether it is on the higher side or the lower side. That technical intelligence would be useful here in making choice here. Okay. Now let us see how to analyze this in Minitab. We have 11 minutes more, so I'll just show you the procedure for CCD in Minitab. So I just go to Minitab and start DOE. Here in Minitab, you have response surface as the another tab here, or menu there. Create response surface design, central composite. Okay, and you also have box banking. And the number of continuous factors also you can give. There can be categorical factors also can be given. And then we have available designs here. So central composite design, full, half, quarter, and 8. So you can also do the various types of designs. So for 2 factors, you can see here only full is available. For 5 onwards, you can see half. So in that also you can reduce the number of runs. So these are the unblocked is 13. So we should be choosing this particular part here. And box banking designs are also available. So this gives you a choice. And then we go to design. So we make choice of full 13 runs. So center points, total points are 5, cube points are 0, and alpha is 1.41 here. So, and number of replicates we are putting 1. So this is click OK here, and we go for factors. So factor here is time, and here it is temperature, and I guess the time is 80, 90, and temperature is 165, 175, 80, 90, 165, 175. So these are the cube points that I'm defining here. And options, I won't randomize the runs. Click OK and click OK again. What is in the result summary table? That's okay. Click OK here again, and I get the design here. So this is the design that I get. Okay. So the point type are given here. So these are the factorial points. +1 are the factorial points, and the minus are the the actual points, the star points basically. So you can see here the start points are given here, and then you have the center points here, 5 center points. So that's how it is given. Now the interesting part here is that we are not restricting ourselves to only one response. We are making we are taking 3 responses here. So yield, viscosity, and molecular weight. Okay. So I will copy these particular responses, and then we will analyze this design for yield, viscosity, and molecular weight separately, and then see how the optimum region and control plots, etc., can be plotted. Okay, so I go to Excel sheet here, and then these are the responses that I got. Yield, viscosity, and molecular weight. So only thing is that I need to be careful. I have these center points here, which are to be removed. Wait. Sorry. Give me a moment. How is the sequence here? 79.9 80. Yeah, I'm good to go. Fine. As of now, this helps. Okay, so this is it. I'll just see once again whether I am goofing something or not. Give me a moment. This should match. And this should match with the tab as well. Yeah, I'm relieved. Fine, no problem. So I have this design, which is now what I do is I need to analyze this design. Okay. Add DOE response surface and analyze response surface design. And the response is yield. I can analyze this at a time, or I can analyze this separately also. Right, for the time being, I will just analyze this. Now here, now look at this. Now what are the options available? Full quadrant, linear, linear plus square, linear plus interactions, and full quadratic. So these are the 4 options available here. Now full quadratic means it will have linear, it will have interactions, and it will also have the square terms. Square terms means the non-linear terms here. Okay. So for example, A, B are the linear terms. A is square term, B is square term, and that makes this non-linear. So full quadratic is being used, and this AB is the interaction that we have. So full quadratic means full all of the terms. So if you wish to use only linear, it will be only this. If you used to use linear and squares, it will be you are not including interaction here. If you are using linear and interactions, it is only this. If you are using full quadratic, this is how it will be. So I'll use this, and graphs, I'll say residual 4 in 1, and click OK, and click finally OK, and I would get 3 responses here. Okay, so I'll just go to the PowerPoint slide and explain it there. So this is what I just did. So select 4, and this is what you would get. So this is for yield. So yield, we get certain equation here, and you can, if you just see here, except this interaction, reaction time and temperature, rest all are significant. Okay, and this is the equation that you got for yield. We go further and look at the R-square values, they are good. And this is analysis of variance for yield, which is already given. Note that p-values for regression linear square are very low, showing high significance. And lack of fit here, 0.29, is not significant. Thus, the model is reasonable fits. So that means lack of fit means if this is significant, that means the model is not fitting. If this is not significant, that means the model is fitting. So it is negation. So lack of fit means what? If this is the relationship that we have, this is your actual point, central point, corner points, and the actual points, and center point. Here is the center point wherein you are expecting that it is going to have the maximum. So if it is a good fit, then the difference between the fitted curve and the actual curve is actual points is not very high if it's a good fit. Okay, so that's how it is done. So these are the residual plots for yield. Then you are doing it for viscosity. You can see for viscosity, reaction time, this square term is insignificant. Reaction time is insignificant, and this interaction is insignificant. We can remove this from the model, but that needs to be done separately. And then there is molecular weight, and for molecular weight, you can find the p-values are not significant at all. So model is not a good fit for molecular weight. We can reduce second order and interaction terms. So we will not use this at all. So this can be reduced. Okay. So we will now do that, and then after that we will do the surface plot. Okay. How much is the time left? Oh my God. Are you allowing me for 5 to 10 more minutes? Is that okay?
Yeah,
Yes, sir. Yes, sir. Go ahead. Yes, sir. No issue.
Because that is the only, I mean, I will not cover box banking, but I'll just talk about it little. But I just need to cover this. Just allow me some time. I'll
Yeah.
not take much of your time.
Yes, sir.
Okay.
Yeah.
So, I need to, now analyze this. So I have got the response surfaces, 3 response surfaces here, and 3 responses, and their analysis is done. So as I see here, I need to reduce the model. Now for reducing the model, I need to again go back separately. So I go to Stat, and I go to DOE response surface and analyze response surface design, and at a time I will only take one response. And the terms here for you can see here that this interaction is not significant for yield. Okay, so from here I will reduce the interaction. This I will remove from this and click OK and click finally OK. So this is for the yield. Now for second one, viscosity. What I need to do is, so for viscosity, if I just, sorry, for viscosity, this is for viscosity. What is not significant is the square term here. So time is, so AA needs to be removed and AB also needs to be removed. Okay, so I say for viscosity terms, AA needs to be removed. So this is removed here and I click OK. And for the third one, the molecular, I am square terms and interactions, all I am removing for molecular weight. So now, yeah, this interaction also needs to be removed for. Okay, and click OK and click finally OK. So now the models are reduced. Now what we need to do is we need to perform the contour plots and surface plots. So we would get the contour plots like this for, and you can see how the optimization can be done. So let's now go to the contour plot plotting. So I go to stat, I go to DOE, response surface and contour plot. So here I am first doing it for yield, okay, and time, temperature, contours, all okay. So click OK, and finally I get the contour like this. Now if you wish to see the surface plot for this, so I know it is very interesting. Surface plot for yield. Yeah, there you go. And Minitab gives you, it can, you can see the surface. You can rotate this and the surface can be seen. Yeah, this is how it was. You can have the bulb also to, see the surface. So, I mean, there are features available. I don't wish to get into the features, but that's how it is. Okay, so I do it for the molecular weight, sorry, the viscosity now, and we can find this out. This is the contour plot, sorry, the surface plot for, look at how the response surface of viscosity is, and I can show you the response surface contour plot for viscosity as well, and now you will be able to see that, which looks like this. Okay, so this is the contour plot, and finally we have response surface for the molecular weight. Click OK, and this is the surface which is quite linear. So I don't wish to show the contour plot will be sorry, the contour plot will be somewhat like this. Yeah, here we go. And this is the molecular weight, and it will be simple contour plot like straight line. So we have 3 contour plots drawn. Okay, so and surface plots also we have seen. Now what we need to see is we need to do the optimization. Okay, so optimization I can do for all the 3 together, or only for yield I can do that. Multiple responses also I can and I'll show you that directly. And then we can have the overlaid control plot, and then we'll stop for the day. Okay, so I go for stat DOE response surface, and then there is this star response optimizer. And molecular weight, I wish to just a minute. Yeah, I just put these values. Sorry, I don't think that's possible. Oh, that's for multiple responses, overlaid control plot. Fine, I think we directly go for the overlaid control plot. Multiple response optimizer is possible. Yeah, maximize, target, and minimize. Sorry, I should have seen this. Molecular weight, I am trying to minimize that. And viscosity yield, I am trying to maximize, and viscosity I am keeping at target. And the target here is 65 for, and I then set up this. So molecular weight, I am keeping upper value as 3400 and target value as 3200. Viscosity, I'm keeping it as 62, 65 as target, and here 68. And molecular weight and yield, as expected, this is at 80, and yield at lower is 78. This is the minimum yield that I want. And I click OK, and then options. Yeah, there are no constraints that I give. And results, solutions, I can have multiple solutions, but right now I'll keep it to one for time being. And this is what I get, the optimum response. So this is the 85 and 166, and this is the molecular weight, response, viscosity, and the yield. So for all of these values, this is what I get. And the desirability, composite desirability, 70% of my target is achieved. Okay, 70% of the expectation is achieved, is I would say. So this is the relationship. Molecular weight, you can see that was straight line. The viscosity here was, temperature is with respect viscosity is like this, and yield with respect to time was non-linear, with respect to temperature also was non-linear, and you get these values. Okay, so this is the optimum value here. Okay, now there is an interesting thing and that interesting thing is last part, and that is overlaid control plot. Now here all these parameters are, we are going to select all of this. All these responses needs to be seen, and then we are going to overlap all these control plots and see the overlaid control plot. So first is molecular weight, which is 2900. This is the region that I am interested in, 2400. Sorry, 3400. Then viscosity is 62 and 68, and yield is 78.5 and 81 and click OK. And I get options I don't need. I click OK and I get a core control plot like this. Now this region, this is time and temperature. Now this is my design region. This is my design space. Okay, so this circle is for yield. And this particular quadratic line is for viscosity, red. And this straight line is for molecular weight. And this is the region which matches with my expectation. Okay, so this is the design space, and anything between this will give me yield between these two lines, viscosity between these two, and molecular weight between these two. So I can have the design space like this. So somewhere between this time temperature, this is the region which will meet all my expectations. And that's it, friends. I think I won't be able to give justice to box banking design. So I wish to stop at this point. I have taken 12 minutes more. Over to you for questions or.
Sir, one question regarding the R square means if R square is more than 80% will be as considered as a thumb rule for the good model, or means how it will be interpreted.
It only shows that there is a strong relationship. It's definitely a good model and the predictability will be very high. So it shows that there is a strong relationship between X and Y.
Hello, sir.
That is the indication. But I have seen processes where R square is low and it still works well. Okay, so I have worked with R squares which is around 50 to 60% low R square values, but experiments are done and they are giving better results than what I was getting earlier. So it for business purpose it might work, but for statistical reason you can have your own reservations for saying that whether it is a good model or not. So for business purpose it might work, but statistically it is still not having good relationship. So it is preferred that you should have more than 80%, and it is likely that but for business reason you can work on that. Hope that answers your question.
Okay, sir. Thank you.
Yeah.
Hello, sir.
Yes,
Like
please.
for some of the factors, we give a increment of, let us say, 2 degrees. So it may depend on criticality or the expertise or the resource constraints, etc. Right?
Yes.
Okay.
So I have given here by 2, and that was coming from the slope that we have got. Okay, so
Okay.
so we decided 5 increment on the time was our choice. So if I choose it to be 10, it could be something different. I mean, so but you can choose it for one factor, and for other factor it has to come from the slope.
Okay, sir. Okay.
Yes. Yeah.
Sir, the standard order, the experiments can be conducted in any order, right?
Yeah. I mean, yes, it can be done. For randomization, it can be done in any order.
Okay, sir. Thanks for
Yes.
excellent tips, sir. Thank you.
Yeah.